Okay, so today we're looking at a common physics problem where you have to take the component vectors of a vector in order to do this math correctly. So these problems can be really tricky, and a lot of it has to do with how they're worded, and there's a lot of trigonometry involved. So let's look at this problem here. A plane was flying 350 meters per second, 88 degrees west of north, and then it hit some wind. It ended up flying 300 meters per second, 66 degrees west of north. What was the velocity of the wind that caused this change? Okay, so let's try to draw a picture here. So the first thing you want to do with these types of problems is you want to create an XY coordinate plane, because all of this is going to be based around a position on an XY coordinate plane. Okay, so looking at this, the first thing you want to understand is where are west, north, east, and south? Okay, so when the problem says that the plane was originally flying 88 degrees west of north, what you do is you go to north, the of part, the of north is where you start, and then from there you go 88 degrees west. Okay, so you're looking at a vector that looks something like that, where this is an 88-degree angle, and that's because you're going west of north. Okay, if it had been, for example, 88 degrees south of east, you would be looking at east, and then you would be going 88 degrees south of east. Okay, so that's the first part that's important to understand, is how does this coordinate system work? Okay, so let's go ahead and draw a vector that represents our plane. So our plane is originally going at 350 meters per second at 88 degrees west of north. So this is an 88-degree angle right here. And this plane, this vector, has a magnitude, or a speed in this case, of 350 meters per second. Okay, great. Then the problem states that after it's originally flying for some amount of time, a wind hits it. It experiences some wind, and it ends up flying at, I'm going to actually change where this is. This is still an 88-degree angle right here, but I'm just going to write it over to the side, 88 degrees. After it hits the wind, it ends up flying at 300 meters per second, 66 degrees west of north. Okay, so I'm going to draw it after it hits the wind in green. So it's going to go a little bit slower. The magnitude's going to be a little less. And the angle away from north is also less. This angle right here is now only 66 degrees. Okay, so somehow the plane has shifted over towards north. It has gotten more north in direction. And the only way that that makes sense is if the wind that's hitting it is hitting it from this angle, right? That's the only way that the plane is going to be shifted over towards north. So we know that the wind must be coming up from this direction. Okay, and so what you can do at this point is you can create another coordinate plane, this time right at the terminal position of your original vector. And you can say that there's now a new vector, which represents the wind, coming up like this. Okay, and we don't know what the magnitude of that wind is. That's what we're trying to figure out. Okay, we also don't know what angle it's coming at. That's what we're trying to figure out. So to set up this problem, the first thing that you need to know is what is west of north, right? So 88 degrees west of north, you start at north and you go 88 degrees left. Okay, then we need to know that based on its new trajectory after it hits the wind must have been coming from the bottom left up to the top right. Okay, so now where's the math involved in this? This is just the initial setup. So here's the math. The first thing you want to do is you want to break the purple vector, the initial trajectory of the plane, into its components, right? So I'm going to redraw a coordinate plane with that vector. Okay, great. So I'm just redrawing this. So here's 88 degrees. Now, if that's 88 degrees, then we know this right here is 2 degrees because that is a right angle on that quadrant. And so you just do 90 minus 88, which gives you 2 degrees. And then what you want to do is you want to break this up into its vertical and its horizontal components, okay? So to figure out its vertical component right here, its velocity in the y direction, all you would do is you would say that the sine of 2 degrees is equal to Vy, the velocity in the y direction, over 350. And that's just using SOHCAHTOA, which is how you solve for sides of unknown sides of right triangles using trigonometric functions. We know that the sine of whatever this angle is, the sine of this angle right here is equal to the opposite side divided by the hypotenuse. Now, I didn't write it in, but we know that the hypotenuse is 350 because that's the speed of the plane. That's the magnitude of the vector. Okay, and then you can just solve for v sub y. So v sub y would be equal to 350 times the sine of 2. And if you use a calculator, which I'll do now, make sure you're in degrees on your calculator. You get that v sub y is equal to 12.2 meters per second. Great, and now you just want to do the same thing for the horizontal component of that velocity. Okay, so for the horizontal component, you'll say that the cosine of 2 degrees is equal to the horizontal component v sub x over 350. And then you just solve v sub x equals 350 cosine of 2. Once again, use your calculator, making sure you're in degrees. And you get that v sub x is equal to 349.8 meters per second. Great. So now we've got our original components. Now we need to do the same thing, but for the altered trajectory of the plane after it gets hit by the wind. So let's go ahead and do that now. Let's create another coordinate plane. This is 66 degrees, and if that's 66 degrees, we know that this is 24 degrees because 66 plus 24 is 90. We know that this green line has a magnitude of 300, this vector, and we can break it up into its components, looking for v sub y and v sub x. Oops, that's x. Okay, great. So you just do the same thing again. So we can say that v sub y is equal to the sine, or let's do it the other way. We can say that the sine of 24 is equal to v sub y over 300, or v sub y is equal to 300 sine 24, which is equal to 122 meters per second. Then we do the same thing for the horizontal component. We can say that the cosine of 24 is equal to v sub x over 300, or v sub x is equal to 300 cosine of 24. And we'll do that on a calculator. V sub x is equal to 274.1 meters per second. Okay, great. So now we know the vertical and horizontal components of the original trajectory. we know the vertical and horizontal components of the new trajectory after it hits the wind. And notice this is all based off of trigonometry, right? All I'm doing is right triangle trigonometry to figure out what these components are. Now we have to put in our wind, okay? So we know, let's look at what's happening. Originally, we're going from a, let's write this in, a horizontal trajectory of 12.2 meters per second, or sorry, a vertical, and a horizontal trajectory of 349.8 meters per second. And then what happens? We end up with a vertical trajectory of 122 meters per second and a horizontal trajectory of 274.1 meters per second. So what's happened? In the vertical direction, we've sped up, and in the horizontal direction, we've slowed down, right? So we've subtracted some from our horizontal, and we've added some to our vertical, okay? So now what we need to do is we need to figure out what are the horizontal and vertical components of the wind, where W represents the wind vector. Okay, and what do we know about vectors? That you can either add or subtract them to get from an initial vector or to a final vector. So if we look at our initial vertical vector of the plane, v sub y, and we add our wind vector to that, plus wy, that should give us our new vertical vector of our plane, v sub y. Okay, how did I know we add the wind vector? Well, it's because we're going from originally being 12.2 meters per second in the vertical to 122. So we've added a vertical component to it. Okay, and now we can do a similar equation, but for the horizontal, where the horizontal initial vector of the plane minus the wind is equal to the new horizontal component of the plane. And how did I know it was minus? Well, if you look at it, horizontally we start at 349 and then we get to 274. So we must have subtracted some from that, right? Okay, so now let's just put some numbers in here. We know that the, let me use a different color. This becomes, so v sub y was 12.2. So 12.2 plus wy, which we don't know, is equal to 122. And then our second equation is 349.8 minus wx is equal to 274.1. Okay. And now, and you know what? I said this is a minus, but let's actually do it as a plus. And then when we get a negative number for wx, we'll know that that negative number just means something. And what does it mean? It means the direction of the wind. So we'll do them both as pluses, which is just going to give us a negative number for wx. Okay. So let's go ahead and solve this now. So wy is equal to 122 minus 12.2, which is 109.8. And our wx is equal to 274.1 minus 349.8, which is negative 75.7 meters per second. Okay? Okay, so what does that mean? That means that if I were to look at a coordinate plane for the wind, I know that the wind in the vertical has a displacement of a vertical component of 109.8 and a horizontal component of negative 75.7. Now, what does that negative mean? And I don't want this to be confusing. That negative means that rather than going this direction on the x-axis, because we originally defined left on the x-axis as positive, it means that this wind is actually going right on the x-axis. Right? We said at the very beginning that this way was positive for x, right? Because we had a positive trajectory here, and that was going to the left. Same thing here. This is a positive, and it was going to the left. So now if we get a negative number, all that simply means is that the wind is going to the right, okay? So that means that our final vector should look something like this, where the arrow, the vector arrow indicating which direction it's going, is that way. Okay, so it's moving from bottom left to top right. How do we figure out the magnitude of that vector? Well, it's very simple. You just use Pythagorean's theorem, right? So W squared is equal to 109.8 squared plus negative 75.7 squared. So W squared is equal to 109.8 to the power of 2, 12056.04 plus 5730.49. Add these two together, W squared equals 17,786.53. Take the square root of both sides. 133.37 meters per second. So that is the total magnitude of our wind vector, which we got by solving for the vertical and the horizontal components of that vector. How did we get the vertical and horizontal components? Well, we said that if these are the original vertical and horizontal components, and these are the altered, the new horizontal and vertical components after it hits the wind, after the plane is affected by the wind, we can set up these two equations which tell us that the original vertical vector plus the wind's vertical vector is equal to the altered vertical vector. The horizontal vector of the original plane plus the horizontal vector of the wind is equal to the horizontal vector of the new trajectory. All we did was then plug in the numbers that we got in the beginning. We solved for our components of our wind, and then we used Pythagorean's theorem to figure out the magnitude of that wind vector. Now there is one other thing. We need to figure out what direction this is coming from. So we want to figure out what is this angle right here, theta. Okay, so what I'm going to do is I'm going to redraw this triangle so we can figure that out. Okay, so this angle right here, theta, we know that this side of the triangle is 109.8. This is a right angle. We know this is 75.7. The negative is not important because it's just the length that we're interested in. The negative just tells you the direction that the wind is going, right? And we know, based on trigonometry, that the tangent of that angle theta is equal to the opposite side, 109.8, divided by the adjacent, 75.7. And then what do? We do that theta is equal to the inverse tangent, tan to the negative 1, of 109.8 over 75.7. Then you just pop that into a calculator. And you get that theta is equal to 55.4 degrees. Okay, so what does that mean? That means that the wind is going 133.37 meters per second at 55 degrees south of west. Okay. 55 degrees south of west. Now, there are multiple ways to go about that. Now, 55 degrees south of west is essentially the same thing as 35 degrees west of south. Okay? Those are the same thing. See if you can figure out why those are the same thing.